Welcome to Brain Vision.
In this question, we have a bar from A to O here that we would like to find the angular velocity of. So this is going to be a little complicated. There's some mass on a bar that this rotating bar is pushing down on, so it will slide that bar to the left. Point B here will move to the left at the same rate that C is moving to the left. And we would like to start writing all of this in terms of things that we might actually be able to use. So the end result, or what we're looking for, is omega OA in terms of the velocity V. So that'll be how fast S is changing there. The collar position, so that actual position of point C, S, and the height, H. And I have not written the height yet on our drawing, but H is just this distance B is above the horizontal. So we'd like to find a function for this. So first, we can rewrite our velocity B as just the change in S with respect to time. We can then also look at the tangential and normal components to that velocity B. So the tangential component, this will be VBT down, and we'll have a component VB normal along the pipe there. So we can rewrite these then. So VBT will just be the angular velocity times the radius, which will just be the length between O and A. So I could write that as L, but we don't know what L is. Luckily, we can find that using some geometry. So if we know the length of this bar here, L, let me fix that, sorry. Okay, the length of the bar is L there. Then we can rewrite that using some geometry, that L is S times the secant of our angle theta. So VBT is just omega times L, or omega times S times the secant of theta. So that's pretty nice so far. Now we also need the normal component of that velocity. And the normal component of the velocity will be just how fast our length L is changing over time. And the length, I did not draw this on here quite correctly. So let me pause for a second. So this length L should be just that position up to B. So it's the actual position of B along the rod there. So that the normal component of the velocity will just be dl dt, which we can rewrite as we know that L is S times the secant of theta. So we can actually take that derivative then, and this would give us the velocity times the secant of theta plus S times the secant of theta times the tangent of theta times negative that angular acceleration. So the next step then, we can calculate the total velocity by first looking at the Pythagorean theorem that we know that the tangential component squared, VB t squared plus VB n squared has to equal VB squared. So there will be some messy algebra involved here, but we take our VBT, square it, our VBN, square it, and we'll have to use a trig relation that 1 plus the tangent squared of theta equals the secant squared of theta. To get us to the point that omega squared s squared secant to the fourth of theta plus v squared tangent squared of theta minus 2 v s omega secant squared of theta tangent of theta equals 0, which we can factor. So we have that the omega s secant squared of theta minus v times the tangent of theta squared equals 0. In other words, we have omega, I'm going to write this all the way on the left then, equals the velocity times the tangent of theta over s times the secant squared of theta. But we're not quite done yet. We can use some of what we know from that original drawing, that the tangent of theta, so let me write this in a different color so we don't get mixed up. So tangent of theta will equal h divided by s, and then the secant squared of theta will equal 1 plus h squared divided by s squared, which will allow us a little bit more simplification here. So this will be v times h divided by s over s times s squared plus h squared over s squared. So fully simplifying it, we have vh over s squared plus h squared equals omega, and that is our answer.